Okay, so let me continue with 11.4. I was cut off, technology doesn't always work, so I want to continue with 11.4. So 11.4, continue. Let me do more examples about the direct comparison test. So sigma n equals 1 to infinity 4 to the n over 3 to the n minus 1. Alright, so this looks like we could compare it with 4 over 3 to the n, which is geometric, right? Just ignore the constant, which is geometric, and it diverges because the common ratio is greater than 1. So let's see how we're going to start this. We're going to do 3 to the n minus 1 is, we want it to be greater or equal to be convergence, which is, right? It's less or equal, sorry. It's going to be greater or equal when we flip it. 1 over 3 to the n minus 1 is greater or equal to 1 over 3 to the n. If we times by 4 to the n, 4 to the n is positive, and that's true for all n greater or equal to 1. And since sigma 4 over 3 to the n diverges, since it is a geometric series with r greater than 1, that's 4/3. That implies our series diverges by the comparison test, direct comparison test. So the direct comparison test requires us to do a term-by-term comparison, which is not always easy. That's why we're going to need another comparison test. It's called the limit comparison test. It's called the limit comparison test, LCT. Okay, let's see what this is about. So again, we're going to require positive terms. Suppose sigma an and sigma bn from 1 to infinity, of course, are two series of positive terms. That's very important, okay? We're not yet doing negative terms. And that if you do the limit of an over bn, you get L as n goes to infinity, then there are three different scenarios here. The first one, if L, so you do the limit of the ratio of the nth term of sigma an and the nth term of sigma bn, and you get a constant. If that constant is positive, it's a positive constant, then the two series are in tandem, then the two series either both converge or both diverge. So we're doing a ratio instead of a term to term, which is a little bit easier. And if that ratio, when you do the limit as n goes to infinity, if it's 0, if you get a 0 and sigma bn converges, then sigma an converges. So if that's a 0 and the sigma, the known one converges, then the one we want to know converges as well. If you get infinity, and sigma bn diverges, then sigma bn an diverges as well. Now remember, we don't talk about negative value for L. It's not going to be negative because both of these are positive, okay? So that's why there's no negative for L here. So if L is positive, if L is 0, and if L is infinity. All right, so if you look at the next example, test for convergence, sigma n equals 1 to infinity 1 over n cubed minus 9n squared plus 1. If you want to compare this with 1 over n cubed, it's not going to be possible to do direct comparison tests, right? I can't say n cubed minus n squared plus 1 less than n cubed or greater. I can't. It's not doable. Direct comparison test is not going to work. But I can do ratio with 1 over n cubed, okay? I can do ratio and you will see that. So this is my an. So we're going to do bn. sigma n equals 1 to infinity 1 over n cubed. That's my bn. And I'm going to do an over bn limit as n goes to infinity and see what happens. So 1 over n cubed minus 9 squared plus 1 over 1. So dividing by 1 n over n cubed is like timesing by the reciprocal. So it would be n cubed over 1, and that's going to be n cubed minus n squared plus 1, which is, you know, when n is infinity, it's n cubed over n cubed, which is 1. And that's L, and it's positive. So if L is positive, the two series either both converge or both diverge. Well, we know sigma 1 over n cubed converges because it's a p series with p greater than 1. That means sigma 1 over n cubed minus 9n squared plus 1 converges as well by the limit comparison test. Okay. Sigma n equals 1 to infinity n over cube root of 8 and 5. Again, comparing, direct comparison is not easy in this case. So this is my an, and bn that I want to use, obviously I want to ignore the constant. It's n over 8n to the 5th to the power 1/3, and I don't really need the 8. So n over n to the 5/3, which is 1 over n to the what's 5/3 minus 1, 2/3. So I'm going to compare with n equal 1 infinity 1 over n to the 2/3. You can see where I'm getting my b's, ignoring the constants, and then just the powers of n and reduce it. That's known to be divergent, as we know, right? It's a p series. So let's do the limit comparison test. an over bn, which is n limit n goes to infinity, n over 5th root of 8n to the 5th plus 7 divided by 1 over n to the 2/3, which equals limit as n goes to infinity. Again, we're going to times the reciprocal, so we're going to get n to the 2/3 times n to the 5/3 over the 5th root of 8n to the 5th plus 7, which 5th root cube root, sorry, cube root. So that's the cube root. So that we can write this as n to the 5 to the 1/3, and that's to the 1/3 to make it easier. So we have n to the 5 over 8n to the 5 plus 7, all of it to the 1/3, just to make things a little bit more doable. And if you do the limit as n goes to infinity, inside there you get 1 over 8. The cube root of 1 over 8 is 1/2, which is positive. So by the limit comparison test, sigma n over the cube root of 8n to the 5 plus 7 diverges, just like sigma over n to the 2/3 diverges. Actually, this one, I was looking at it, you could do the nth derivative test, and you get it. Oh, it's 0, so it doesn't, it's inconclusive. Okay, never mind. All right, let's do more examples. Example 3, sum from 1 to infinity tangent 1 over n. So the only thing we can compare it is it's with the series. So this is an. We can compare it with the series 1 over n and see what happens, which we know it's harmonic, it diverges. So let's do limit as n goes to infinity tangent 1 over n divided by 1 over n. That's tangent 0, and then 1 over infinity is 0, so we do L'Hopital's rule. So limit as n goes to infinity, derivative of tangent is secant square times derivative of 1 over n, and that's derivative of 1 over n. That all cancels out. You get sine of secant square of 0, which is 1, greater than 0, and since sum of 1 over n diverges, that means sum of tangent 1 over n diverges as well. Alright, sum from n equal 2 to infinity 1 over ln of n. Again, we can compare this with 1 over n because we know it diverges and there's n there. This is an and this is bn. So we're going to do a limit as n goes to infinity an over bn, which would be limit as n goes to infinity, we times by the reciprocal, which would be infinity over infinity. So we do L'Hopital's rule. So that as n goes to infinity, derivative of n is 1 over n, which is limit as n goes to infinity n, which is infinity. And if the limit is infinity and sigma n diverges, then sigma an diverges. And since sigma 1 over n diverges, that means sigma n equal to infinity. If sigma 1 over n was convergent, no conclusion here. N equal to infinity 1 over ln of n diverges as well by the limit comparison test. Okay? And that's the second part of 11.4, and I am done with this.